All right, you can see from the packet, it's kind of a long lesson today. That's okay. Not a big deal. So let's get started on this stuff. Write in standard form, 0.75 billion, simplify that, and simplify the other one. Just exponent rules on 4 and 5. And yeah, there was a 3 and 2, but oh well. So we'll get into the standard form business here in sometime during the lesson today. But you should have been able to do those two pretty easy. Here's our two objectives for the day. I can write numbers in standard notation and scientific notation. I can perform operations with scientific notation. That should be good. And we're just looking at the 4 basic operations today: addition, subtraction, multiplication, and division. So take a minute and copy that down, please. All right, now standard notation, by the way, is just the way we usually write numbers. Like, 1 by itself is considered standard notation. You can have negatives, like -3. You can have decimals, 0.5, and that's considered standard notation. They can be big, they can be small, they can be decimals, they can be negatives, they can even be fractions, but fractions aren't necessarily technically considered standard notation. You can see when we look at standard notation today that we're really talking about the decimal values, not fractions. But scientific notation, if we go back far enough in history, science people got tired of writing really big numbers over and over and over. Right, when you start looking at calculations that involve extraordinarily large numbers, you'd get tired of writing all those zeros or big numbers as well. So they came to math people because they couldn't do it themselves, just like most other things. And math people solved the problem for them. They said, hey, look, you remember how we simplified addition into multiplication? We simplified counting into addition. And we also simplified multiplication into exponents. We can do it for you because without us, you don't exist. And so the math people came up with what is called scientific notation, and the science people rejoiced. Well, the math people rejoiced because the science people were rejoicing. It's a really nerdy thing, for people to rejoice like that, and for those reasons. We also kind of hope that you don't ever get to that point, but perhaps you will. All right? And it's okay if you do, because I'm already that way. So scientific notation allowed scientists to do extraordinarily large calculations very quickly, but then they started looking at extraordinarily small numbers as well, and it allowed them to make those calculations very quickly as well. Of course, today we have other methods to do it, which we'll show you today. All right? So this is a very nerdy way to say scientific notation is this. In fact, this is so nerdy, I'm not even going to read it. Okay? You're welcome to if you'd like, but I assume by the time you read the word magnitude on there, you'd be asleep. Now, there is one thing we need to understand on this. There's what we call significant figures, which science, I guess, stole from math, because mathematically speaking, we'd say, look, if you look at extraordinarily large numbers, eventually you look at numbers that are actually kind of insignificant, right? Like if you looked at like dollars, for example, which we'll talk about today. If you had $1 million and you lost 50 cents, you'd be like insignificant. But if you had $1 million and you lost like $100,000, you'd be like, oh, that's pretty significant. So there's values in these extraordinarily large numbers, and even in just regular numbers that eventually become insignificant. Now, this is the way that we set up scientific notation. There's usually a decimal shown, okay? So that is a decimal. Now, we need to understand place values. Immediately to the left of the decimal is what we call the ones place value. And I feel like I'm spending more time on this than I should, but some people forgot this because, well, I don't even know what grade you learn this stuff. Ones place value. In scientific notation, this ones place value, it's okay to have a value here. In fact, you need a value in the ones place value. It's just that this number, it just cannot be 0. So, of course, that means you could have a 1 there. You could have a 2, 3, 4, 5, 6, 7, 8, or 9. Well, could you have a 10 in the ones place value? Of course not, because you're looking at 2 different place values, for heaven's sake. Also, in scientific notation, you cannot have any values to the left of the ones place value. So, of course, place values would be tens, hundreds, thousands, and so forth. But there shouldn't be any numbers shown here to the left of the ones place value. So again, you need the ones place value. It just can't be 0. You can have any number of decimal values in here, right? So just to review a little bit of the place values, you got tenths, and that's the only real difference here is the th at the end. Hundredths, and I'm wearing a mask, so I'm not spitting on anyone. Thousandths, 10,000ths, and 100,000ths. Well, it's a little moist in my mask now. But after that, then you're always going to multiply this by 10. So this goes back to some history of mathematics. The nice thing about our number system, which is Arabic actually, it's based in tens. So every one of our place values is technically a base 10, even the ones place value, and any of the decimal place values as well. So that's why we show this as multiplied by 10. You're welcome, scientists. And then the 10 is a base, so it should have an exponent right here, some kind of exponent. And you could show this as a box if you'd like, so that doesn't look like a negative. Now this exponent here, it can be negative, it could be positive, it could be fractional, it could be decimal, it doesn't really matter. Of course, if it's a whole value or just an integer, then this would tell us that we're just moving the decimal any number of spaces, okay? Now first off, let's start with positivity on this one. If this exponent was positive, and this is in scientific notation, then you move the decimal to the, and this is crucial, the right. If that exponent is positive, you move the decimal to the right. If it were negative, I don't know, maybe I should put a question mark after that. If it is negative, then you move the decimal to the left. I'll show you. I almost had no space there. All right, and so yeah, what decimal are we looking at? Well, this one right here. This is the key decimal, right? Because base 10s move decimals depending on the sign of the exponent right there. Now, so now that we know if it's positive or negative, which way we would move the decimal, the number inside, or the number that is the exponent, tells you how many times you would move the decimal, okay? So this is kind of the foundation of scientific notation. And so hopefully after you figure this out, you can rejoice as well. All right, we're going to come back to A, B, and C, but let's do E, F, and G first on this one. So let's start with E. So this is a standard form number. It's just a number written in its standard form, 5,320. But we're going to write this in scientific notation. Now, remember, with scientific notation, you got a decimal here. And we should only have a non-zero number in the ones place value, which means that our first non-zero number to the left is 5. Okay, so that would be 5, 3, 2, 0, like this. And then, of course, we'd multiply this by base 10. Now, we'll get to the exponent here, but notice this is 5.230 now. And when you have trailing zeros, like we do on this one, pretty much just get rid of those. So what we would really want to see on this is just 5.32. The 0, while it holds a place value in standard form, it's not necessary to hold that place value in scientific notation. Well, let's go up here to the number, 5,320, okay? We're going to put the decimal between the 5 and 3. It used to be right here, right? So in calculating the exponent, we just look and see, well, how many times did I move that decimal? Or another way to look at it is how many place values are between the decimals right there. 1, 2, 3. So I have an exponent of 3. Now, this is a positive 3, particularly because the number that we were looking at originally, the standard form number, was greater than 1. If, and we'll see this in some examples, if that number is less than 1, then we would use a negative exponent, okay? But as of now, this is our final answer right here. So that's kind of one way to look at it. I'm going to show you a different way, although it really ends up being pretty much the same way as well. If by chance this was a negative right here, not that it is, but if it were negative 5,320, you just have a negative number in front. Notice that the negative here is the base. It's not part of the exponent. Negative exponents tell us something very, 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 very different. All right, now we did that one way. 420,000. Now this is just a different way. I'm going to write the actual number, 420,000, right? Now, well, maybe it's not so different. I'm just kind of looking at a different. I would look at the first non-zero number farthest to the left, which in this case is 4. I know that has to be my ones place value, which means the decimal has to go between the 4 and the 2 on this one, right? Now, any of those trailing zeros I can get rid of at this point. Not that you have to at this point. You can get rid of them at any point. But I know I'm going to be multiplying by base 10. But what is the exponent? Well, then we go back to that number up there. See how the decimal is between the 4 and the 2? Whereas it used to be right after that last 0. So how many place values are between the two decimals there? 1, 2, 3, 4, 5. So that means our exponent is 5. So it ends up being 4.2 times 10 to the power of 5. You know, I don't know that strategy was very different from the first one, but we can call it different, I guess. Well, G's pretty big, but it's no problem, okay? So on this one, and I guess we'll work with the number directly. And yes, I have it already written. I know that our first non-zero number to the left is 9. So the decimal will have to go after that 9, between the 9 and 0. So, as a decimal, this will end up being 9.04. Now again, I'm not showing any of these zeros trailing. Why am I showing this one? Because it's stuck between two non-zero numbers. If there was only zeros, like we do here at the end, then we get rid of those. But if it's sandwiched between other non-zero numbers, keep those zeros, all right? And yes, we do need to multiply this by base 10. Now the decimal used to be over here. We moved it to where it is in purple there. So the exponent of 10, let's see what that is. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a power of 9. And that's positive 9 again because our original standard form number was more than 1. So here's our final answer. Now again, we'll get to A, B, and C here in a moment, but I just want to start practicing because we should be pretty familiar with standard notation numbers. But this is how you change them into scientific notation. All right, on these examples, the only thing that we see that's different, and we're going to start with these three, is that we see these numbers are less than 1. Remember, since these numbers are less than 1 as decimal values, then we're going to be using negative exponents. So, starting with E, well, we got 7,500 thousandths is what it looks like. And we know the decimal, that would be a little bigger, that seems better. The decimal is going to go right after the 7, right? Right between the 7 and 5, which is going to make the decimal value in scientific notation 7.5. Of course, it's still multiplied by 10. And yes, this is less than 1. The original standard form number is less than 1, which means the exponent is negative. So I'm putting that negative already into the exponent. I just got to see how many place values are between the decimals. 1, 2, 3, 4. So it ends up being an exponent of negative 4. And this is my final answer, 7.5 times 10 to the power of negative 4. Now, is it possible that you could check this? Yes, there is. But I'm going to wait. I'm going to wait till the third example to talk about that. All right, same thing on this one. Again, we have it written in standard notation. Let's figure out where the decimal goes. Remember, in the ones place value, it should be a non-zero number, so I can't use any of those zeros. But the 4 I can use, so that's where the decimal would go, right after the 4. Which would then make that 4.005. And then, of course, we're going to multiply this by base 10. Once again, that original number is less than 1, so it's going to be a negative exponent. That's a negative there. But how many place values are between the decimals? 1, 2, 3. So I end up with a negative 3 exponent of base 10. And once again, this is our final answer right here. Now, do be careful because 0.4005 times 10 to the power of negative 2, it's equivalent but it's not formal scientific notation. And I mean, if you've ever seen a math person freak out, it's not pretty. But if you show that to another math teacher, they're going to freak out about that stuff. I'm not as picky, which sometimes I think is a pretty good thing, actually. It shows a lot of zeros. It really shouldn't be a problem. And again, this is kind of the convenience, especially with an extraordinarily small number like this one, of scientific notation. So I'd look at this and say, look, the decimal has to go between the 9 and 2 right here, right? Which is going to make that 9.2 times 10 to some power, right? Because we're changing this into scientific notation. And we see the two decimals, where it was originally and where we need it to be placed for scientific notation. Now, the number originally was less than 1, so I know the exponent's negative, just like the previous one. But the value of that negative is how many place values are between the decimals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that exponent becomes 10, but negative 10. And so this is that value in scientific notation. All right, so there's those three. And yeah, you can write them in these boxes if you'd like, but whatever. It's the same answer. Let's get to these three. 4.2 times 10 to the power of negative 8. All right. Well, I'm going to rewrite just the decimal, 4.2. Now, remember, if you have a negative exponent, this tells us that we're going to move the decimal to the left. How many times? 8 times, right there, right? So I'm going to move it to the left 8 times. I'm going to need more space on that 4.2 actually, so I'm going to put it over here. That's better. All right, so 8 times to the left. 1, 2, 3, 4, 5, 6, 7, 8. Perhaps I should have given myself more space. Now, there's some empty place values now, which if you have empty place values, just put zeros in there. So what is that? 7 zeros right there. So I end up with 0.1, 2, 3, 4, 5, 6, 7 zeros, and then the 4, 2. And this now is in standard form. So this also means if we saw a positive exponent, just like we talked about in that previous slide, is you'd be moving the decimal to the right. Of course, it won't show the positive sign either. On this one, once again, the exponent's negative, so we're going to move the decimal to the left, particularly 7 times. So I'm going to write 8.12, the decimal value from scientific notation. Then I'll show the movement of the decimal to the left 7 times. There's one place value, 2, 3, 4, 5, 6, 7. So that's where the decimal will be. Any empty place values become zeros. Bam. So this ends up being 0. How many zeros is that? 1, 2, 3, 4, 5, 6 zeros, 8, 1, 2. And now this is in scientific notation. Sorry, that's standard notation, my bad. All right, C is going to work the same way. Let's write the decimal value here, 7.625. And again, this is a negative exponent, so we're going to be moving the decimal to the left. And once again, 3 times, right there. So let's take that decimal, move it to the left. 1, 2, 3 place values. There it is. Any empty place values become zeros. I like to show that 0 in front just because it's pretty. I should have given myself more space though. But this ends up being 0.007625. And there it is. Standard form of that original scientific notation number. Now something else I want you to realize on these, and we've said this before about mathematics, particularly with fractions, we emphasize it in fractions, but scientific notation is a way to show a number just in a different format. So we're not changing the value of these numbers. All we're doing is changing the way they look. That's all. So the more we get used to this, the more we can communicate these in equivalent ways, but it may sound different, okay? But it is still the same. Let's do these three here, A, B, and C from that previous table. All right, so once again, here I have a positive 8, so I'm going to be moving the decimal to the right, particularly 8 times. So I look at 6.345, just write the decimal as is, and then I move the decimal to the right 8 times. 1, 2, 3, 4, 5, 6, 7, 8, and again, any empty place values get zeros. So what do we end up with this? So 6, 3, 4, 5, and then I counted 5 zeros. 1, 2, 3, 4, 5. And then yes, some people prefer to see the commas to show each period. So that's 634,500,000. We did it. Or part B. Well, let's write the decimal, 8.04. That 4 exponent of 10, base 10, is positive, so we're going to move the decimal to the right once again. 4 times in this case. 1, 2, 3, 4. Any empty place values get zeros. And so to rewrite this, you'd have the 804 and then the 2 zeros in green, which makes this 80,400. All right, part C, let's write the decimal, 4.26. But our exponent being 5, positive specifically, means we're going to move the decimal to the right 5 times. So that'd be 1, 2, 3, 4, 5. Any empty place values get zeros. So we end up with 4, 2, 6, and 3 zeros, which, from what I can see, makes that 426,000 right there. Let's try this one. We're going to take the calculator. It appears to me that's 5,555,555,555. That's 10 fives. So I'm going to type in 10 fives. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fives. And it says multiply by the other one. That's okay. Times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fives. And when I push enter, this is what the calculator shows, at least to me. 3.08641975 times 10 to the power of 19. Now, why did the calculator show us this instead of the actual answer? Because it's saying, look, my screen's not big enough to show you all of the 20 place values, okay? So instead of showing you that it's an error, it's saying, well, we can show it in scientific notation, which, by the way, this is an approximation because it's only showing a certain number of decimal places. But it is in scientific notation. And so, of course, you should be able to change, because you're going to have to do this on the assignment, you're going to need to change a number like this back into standard notation. But, of course, you'd only show, I guess, however many decimal places it's showing you in the problem, okay? So if we kept all these decimal places, we're saying that they're all significant based on the calculation that is being made, but for this one, we don't know why we multiplied these, so it's hard to tell other than to say, well, this is what the calculator showed us, so that's what we'll do. Now, in the past, what you would have seen, and some of you may have seen this on a calculator, depending on which one you got, you may still see these decimal places. You may have seen more or less, doesn't really matter, but instead of showing base 10 times base 10, they'll show E, and then they'll show the 19. This is exactly the same as the scientific notation. It's just shown in a different way. Showing E, the exponent of the base 10 is 19. Again, calculators used to show that. This is called E notation. We're not concerned with that other than that if some of you are using different calculators, you may see something like that on your calculator. But the ones we're using in class, the TI-30XSs, they are going to show scientific notation like this. All right, explain why these numbers are not in formal scientific notation. Well, you look at these and be like, oh, I think I can still find the values of those. That's true. Again, it's not like scientific notation is going to change the values, it's just going to change the way it looks. So what the crap is wrong with these? Well, 402.2 times 10 to the power of 21. Our problem here is that we have place values in the tens and hundreds place values. You can't have that in scientific notation. They shouldn't be there. Okay, so I guess formally this would have been 4.022 times 10 to the power of, looks like 23. That would have been it in formal scientific notation, because again, you can only have a number, non-zero number, in the ones place value. Nothing in the tens or hundreds or anything to its left. So on this one, yes. So we could say that you need a natural number in the ones place value, with zero is not natural. It is whole, by the way, though. So that's our problem with this one. You can't have a zero in the ones place value. So if you made this into scientific notation, you'd have 2.17 times 10 to the power of 3. do be careful. Again, I'm just pointing this out because if you go to some math nerd, most of them are teachers, and you say, hey, look at my scientific notation, but you've purposely done it not in formal scientific notation like these two are in, their head might explode. I feel like I've weaponized what I just said for some reason. Not on purpose, though. All right, the first thing I'm going to do on 8A here is I'm going to change this. Oh, I'm going to show the place values for trillions, and that should help us to figure out how to write this. It's not in scientific notation right now, but I'm going to change it into at least standard notation, okay? So I would start, if you look at the decimal, you'd have a decimal, and then to the left is the ones place value, tens, and then hundreds. Usually people put a comma in between that period. And then you got the thousands period, 1,000s, 10,000s, 100,000s, comma. And then you got millions, so 1 million, 10 millions, 100 millions. Next up, billions, 1 million, billions, 10 billions, 100 billions. And now we're into the trillions right here. Now that would be 1 billion, 1 billions, 10 billions, and then 100 billions there. But we don't actually need that 10 billions and 100 billions. How do we know? Because it's only 9, which is in the ones place value of these trillions. So I'd have the 9 in the 1 trillions, 4, which is showing in the 100 billions, and then the 6 in the 10 billions. Everything else just gets filled in with zeros. Well, that felt pretty good, and I even made it colorful, which makes us feel good inside. But we do not want this in standard form. Up here it says, we want this in scientific notation. No problem. I just take that, oh, that's a 9. 9.46, right? Because the decimal would have to go between the 9 and the 4 there. I'd have to multiply that by 10. And remember, the decimal is where it is. That's where it used to be. How many place values are there between that? Well, let's just count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I got 12. That's positive 12. Okay, it's staying. Why is that positive 12? It's because our trillions there is bigger than 1, so it's a positive exponent right there. All right? So that's our answer right there. Oh, by the way, I forgot one thing actually in kilometers. Some people say kilometers, whatever. For these 4 problems, though, let's get these middle 2, okay? All right? Now, here's what they want usually on problems like this one. Let's start with number 4, all right? So, what we're going to do is I'm going to show you how to do this because this is the way that scientists would do it because they're usually dealing with extraordinarily large numbers. Although here, well, what are we looking at? Millions and 10,000s, it looks like. I'm not going to do that, though. So, yeah, and someone said, yeah, if you change this into standard form, then multiply, could you change it back to scientific notation? Yes, you could, but I have even a better way to do it than that. It's not this way, by the way, for me anyways. Some people like this method. So what I'm going to do, since it's all multiplication, is I'm going to use some commutative property of multiplication and say I'm going to take the 4 and 2, move them close to each other and multiply them. 4 times 2 is 8. I can do the same thing with base 10, so base 10 to the power of 4 times base 10 to the power of 6. Why would I do that? Because the bases are the same, and when I multiply bases that are the same, I just need to add the exponent. So that'd be 4 plus 6 right there, which would end up being base 10 to the power of the new exponent is just 10 right there. So it's 8 times 10 to the power of 10. Now, this ends up being, for us, already in scientific notation. Some people like to see the 8.0, and that's good. You don't really have to put that 0.0. You wouldn't have to do it on the assignment. However, when you do it like this, you won't always end up with scientific notation right away, so you would have to maybe move the decimal a little bit more or less, and then you would have to change it into formal scientific notation. Same thing on number 7, but I'm going to show you the second method for me, okay? Now this one can be extraordinarily complicated depending on some of your background, just like I guess all math is. But for me, I like this method because it's called calculator method. So with the calculator, I'm going to type it in exactly like I see it. Open parentheses, 7.2 times 10 to the power of -4. I get out of exponent mode and I close my parentheses. Open parentheses, a new one, 4 times 10 to the power of -9. I close my parentheses, I push enter, and my calculator shows 2.88 times 10 to the power of -12. Okay, that's good enough.
The answer is which one is harder? Which one
Do be careful, because in the future, if you're like, I'm going to use my calculator to do this, some teacher's going to freak out like, why would you do that? That's a horrible thing to do. And it's like, see this thing? It's called a calculator. I'm going to use it. Okay. Here's another 4 problems. However, I'm going to focus on these 2 right here. Number 11. Now this is a division problem, particularly with the fraction, and the calculators we have here in class will give us the ability to put this in as a fraction. That's my n over d button. So I push it. In the numerator, I have 4 times 10 to the power of 4. I go to my denominator and I type in 2 times 10 to the power of 6. And I push enter. What does my calculator give me? Oh, that's not good. 1 over 50. Remember, fractions are not good for scientific notation, but I can make the calculator changes into a decimal. Just right above the enter button, push the double arrow button. Push. And it gives me 0.02. Okay, I can work with that. We can change that into scientific notation. That's not even too bad. I know the decimal has to go after the 2, which would make that 2.0. Not that you have to show the 0.0. I'd multiply that by 10. And then again, the exponents, how many place values are between the decimals, which is 2. Now be careful, because remember, the 0.02 is less than 1, which means the exponent should be negative. And so we end up with 2 times 10 to the power of negative 2 as the answer to this division problem. All right, now, of course, you're still welcome to do this by hand, but I really like calculator method. So, n over d, 5.8 times 10 to the power of negative 6. In the numerator, I go to the denominator, 2 times 10 to the power of negative 3. Enter. And it gives me a decimal. That's okay. 0.0029. I can change this by hand into scientific notation. I know the decimal is going to have to go after the 2, between the 2 and 9. 2.9 then, times 10 to some power. The exponent would be 123 right there. And again, this number originally was less than 1, so I know it's a negative exponent right there. So we end up with 2.9 times 10 to the power of negative 3. So there's those 2, and they're very colorful, very pretty. Yeah, skip number 19. Let's look at 18 first. All right, let's go and do this by hand. Nope, I said that wrong. Let's do this with our hands on the calculator. In parentheses, 4 times 10 to the power of 4. Get out of exponent mode. I push close parentheses. And why am I using the parentheses? Just because I want the calculator to know very clearly that I want this in order of operations, because the calculator is going to think order of operations. And in some cases, it may do it out of the order depending on how it's typed in. So I am using parentheses on this. Plus, parentheses, open parentheses, 2 times 10 to the power of 4. Now, the exponents are the same on this. That's not significant when we're putting this into the calculator. It gives me 60,000 right there. But we do want this in scientific notation. So I put the decimal between the first 6 and the 0, 6.0. You can just make it 6 times 10 to the power of 1, 2, 3, 4. And that's a positive 4 right there, because the number 60,000 is bigger than 1. That's pretty crucial. Some of you guys are saying that we just took the 4 and 2 and added them together. Yeah, that's only the case when the powers of 10 are the same in scientific notation. If they were different, what you're going to end up having to do is change these, or at least most of the time people change these into standard notation and then add, and then replace back into scientific notation. I prefer calculator method, which is why I did not discuss that before. All right, so that takes us through 3 operations: multiplication, division, and addition. Of course, subtraction. So let's do this one with our hands on the calculator. So open parentheses, 9.2 times 10 to the power of 8, close parentheses, minus, open parentheses, 4 times 10 to the power of 8, close parentheses, enter. And that's what my calculator shows me. 5, 2, 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. You can put commas in there if you'd like. So that looks like 520 million. And remember, the decimal for the black number there is right there, okay? But for scientific notation, it needs to be between the 5 and 2. A non-zero number in the ones place value doesn't matter about the decimals. And like we said before, it's no need to show all these zeros here. I suppose you could, but don't do it on the assignment either. So times this by 10 to some power. It's bigger than 1, so it's a positive exponent. How many place values are between the decimals? 1, 2, 3, 4, 5, 6, 7, 8. So we end up with the power of 8. And this would be our final answer on this one. Now I know up here it said do not convert to standard form. We're going to pretend like that wasn't there. So you're welcome to if you'd like. I mean, we did it right here, but again, that's a valid method if you do change these into standard form and then perform your operation and then change it back to scientific notation. That's okay. So that's crucial to understand is especially when they're the same. We're saying that we're dealing with the same place value in scientific notation. It's just doing it in a different way. Like this would be 40,000 and 20,000. Well, you're dealing with the 10,000s here and 10,000s there, which only works, again, if the exponent for your base 10s is the same. If they're different, then you got to change them into standard form anyways and then operate. Or you can just type it into the calculator. Yeah, this is not on the worksheet, but it's a good exercise to help us understand some things, not only about the U.S. debt, but, well, no, it's going to help us understand things about U.S. debt. And I hope from this exercise that you guys start asking lots of questions, not only of adults, but particularly history teachers. They should be teaching you things about where the national debt comes from and so forth, okay? Now, I took this shot of this website, usdebtclock.org, this morning. It's pretty accurate. However, it does not show us what is called unfunded obligations, or I may have that incorrect. But just so you understand that there's what is called unfunded obligations of the United States government, which is like usually it's retirement for people that retire from the government, right? Like teachers, for example. Now, that number, according to what's his name, Davis right there, I forget his first name. But one economist said that the amount of unfunded U.S. debt is up to $200 trillion, and that was like 4 years ago. So that's trillions, by the way. And what are we looking at here? U.S. national debt, 28 trillion, 92 billion, 122 million, 504,009. Of course, it's not showing pennies. Why is it not showing pennies? Because they would be considered insignificant. Well, what is that in debt per citizen? Looks like 85,000, and then debt per taxpayer is even more, because not all citizens pay taxes, right? Some other information that you may find useful on this one is interest per adult. All right, interest. Now, this says it's unfunded debt or interest. It's not unfunded obligations, though, which is what I was talking about before, which is, of course, money that the U.S. government will owe when people start retiring and other things, okay? However, on this one, we're looking at U.S. total interest paid, which I don't know that it's been paid, but it's part of the debt. And we're saying that we're owing some kind of interest to someone. Now, for those of you that have read the Constitution, you know that it's illegal for the government to print money. So, it's like, why do they have to borrow it? That's why, because it's not part of the Constitution. And even that whole system is not really part of the Constitution. For those of you that don't know what I'm talking about, read your stinking Constitution. Also, on this one, it's like, well, if we're paying interest, who are we paying interest to? Well, that's another thing you're going to have to talk to. I would ask your history teachers and see if they know, because if they don't, you should start asking a lot bigger questions, okay?
Isn't inflation?
So, we're going to look at the U.S. national debt in a different way, all right? Particularly because it is so astronomical, let's use scientific notation. But before we do, let's go and just round this to the nearest trillion, which should sound kind of weird, and the fact that we are doing that should raise even more questions. So I'm gonna make this 28 trillion. By the way, when I did this last year with a group of students, it was at 22 trillion. Interesting. So let me see if I got this right. We got ones, thousands, millions, billions, trillions. Yep, that looks good. Now, let's write this in scientific notation. So the decimal would go after the 2, between the 2 and 8. And multiply it by 10 to the power of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 10 to the power of 13. Of course, this is in dollars. So this would be the U.S. national debt in scientific notation. That feels pretty good. However, let's look at another interesting fact. I don't know this from experience because, well, I'm a teacher. However, It's been said, it has been said, that $1,000,000 in stacked $100 bills is 40 inches tall. Now that would be stacked Benjis right there. You take a Benjamin, stack it on top of another Benji, keep stacking until you end up with 40 inches tall. Now you got $1,000,000. Okay. Now, what we're gonna do is we're gonna see how tall is the U.S. national debt in inches. All right.
I don't even want to know.
What I'm going to do is I'm going to figure out how many millions there are in that many trillions. And so what I'm going to do is I'm going to take that and divide it by, well, 1 million. All right? So what do I get then? It'd be 2.8 in scientific notation anyway, times 10 to the power of 7. Inches. That's not inches, by the way. That's just millions. Now, every one of those millions is 40 inches tall. So I take that 2.8 times 10 to the power of 7, and I multiply it by 40. Let's see what we get. 2.8 times 10 to the power of 7 times 40. Enter. And I get 1, 2, 3, 4, 5, 6, 7 zeros. Right there. And this would now be in inches. Right there. What is that? 1,120,000,000 inches? That's pretty good. Well, that's the height of the U.S. national debt in inches. Let me change this into scientific notation, though. 1.12 times 10 to the power of 9 in inches. Well, that's in inches, but what I really want now is feet. So I'm going to take these and divide them by 12. So I divide by 12. It's going to give me a pretty ugly decimal. I'm just going to make that 9.3, and then I'm just going to round that to the nearest, what is that, 3, 6, I guess millionth. 93 million feet right there, which is approximately 9.3 times 10 to the power of 10, looks like. No, sorry, 7. In feet. Oh, that's pretty good. That seems like a lot of feet, which it is. But let's go ahead then and figure out how many miles this is. So I'm going to divide it by 5280. So 93, 1, 2, 3, 4, 5, 6 divided by 5280. And I get 17,613. I'll round that to the nearest 1, though. Well, I'll just keep the 3, just give it the benefit of the doubt in miles, which is 1.76-ish times 10 to the power of 4 miles. Okay? And that's 17,613 miles. Now, if I go to Google, and I say, hey, Google, what's the circumference of the Earth? It says that the circumference, that's all the way around, by the way, is 24,901 miles. Which means that if you were to travel from here, where we are in Utah, and you went the long way around the world to Auckland, New Zealand, that's how long this trail of stacked $100 bills is. Which, by the way, should seem like it's a pretty long ways. Like, we're getting pretty close to making a full ring around the Earth. But again, that should raise many, many other questions, okay? So, we should now feel pretty comfortable writing numbers in standard notation and scientific notation, but also performing operations with scientific notation.